In this video, we are going to talk about normal distributions and then the graphs of different data sets. And we're actually going to start with those graphs first by thinking about frequency distributions and histograms. So usually what happens is we've collected all this data and now we are trying to create a graph of the data so we can see the shape of the data. And a frequency distribution or a histogram is a great way to do that. So we're going to start with frequency distributions. So here we have a data set and they've already organized this into a frequency distribution. So it's telling us download time and they're telling us the number of subscribers. So if we have a download time between 0 and 5 seconds, I have 6 people that would fall in that category or 6 subscribers that fall in that category. 5 to 10 seconds, I have 17 that fall in that category. 10 to 15 seconds, I have 43 that fall in that category, and so on. With a frequency distribution, this one is grouped because we've grouped times together. So we're not just looking at 0 seconds and then 1 second and then 2 seconds. I've grouped together. And I want you to notice that they're equally spaced. So 0 to 5, 5 to 10, 10 to 15, 15 to 20, and so on. So we've got equally spaced groupings down here. So now we can start talking about some of the definitions. Each of these sectors is called a class. So that 0 to 5, 5 to 10, and so on is called a class. When we talk about lower class boundaries, we're talking about the lower end of each class. So my lower class boundaries would be 0, 5, 10, 15, and so on. Just the lower end of each class. And then we could talk about the upper class boundaries. And that's just the upper limit for each class. So 5, 10, 15, 20, and so on. And we could take this and we could create what's called a histogram with that data. So we would have bars that would represent 0 to 5 seconds, and that would have a height of 6. And then another bar, 5 to 10 seconds, which would have a height of 17, 10 to 15 seconds, have a height of 43, and so on. So if we were to do that using some technology, so this first one represents 0 to 5 seconds. 5 to 10, 10 to 15, 15 to 20, 20 to 25 would be represented by this one. And then so on. You can see these heights are going to correspond with our frequency distribution here. So I would have a height of 6 in that first bar, a height of 17 in the second bar. That 20 to 25 has a height of 151, and so on. So I'm just going to write those heights. I'm going to zoom in on this and then write those heights in there so you can see. Let me do that in a different color. So this represents a height of 6, 17, 43, 92, 151, 192, 190, 149, 90, 45, 15, and 10. And what that histogram does is it takes that frequency distribution and it gives us a nice picture to see what's going on. And in this one, you can see that this is approximately symmetric about that middle. So we would say this is approximately normal. normal distributions are going to have that nice bell shape. It would be symmetric about that. If I draw that bell over it. Be symmetric about that middle, which is where the mean would live for that distribution. Now, we could do a frequency distribution in terms of the frequencies or in terms of something called the relative frequencies, which shows us the percent of the subscribers. So the way we would find this column is we would figure out how many we have total. So we would add 6 plus 17 plus 43 and so on. And when I added all this up, I had a total of 1,000. So then we would find that relative frequency by taking that 6 and then dividing it by 1,000, which is 0.006. And if I want to turn that into a percent, then I would multiply it by 100 or move that decimal 2 places to the right. So you can see where that 0.06 would come from. We're going to do the same thing for the rest of them. We could take 17, divide it by 1,000. This finds the relative frequency, or the percent. In this case, it would be percent of subscribers. And then if I move that decimal 2 places to the right, I'm going to get that 1.7. And we would do that for all of those in here to figure out that percent of subscribers. So what's interesting is that that graph's going to be the same regardless of if we use the percent or if we use the frequencies. So you see how it's going to have that same shape here. So this is what's called a relative frequency histogram because it's using those relative frequencies along the axis here. And I've seen problems and in real life where they use the percentages here, or sometimes they'll use the decimal representation. Either one would be fine. There is a benefit to using the relative frequency distribution instead of just the frequency distribution. Remember, the relative frequency is going to be the percent of people that fall in each category, and the relative frequency distribution is going to help you be able to answer some of those questions pretty quickly. So if we were looking at the probability that if a subscriber is chosen at random, that the probability subscriber is going to require at least 35 but less than 40 seconds to download. We could look at our data here. 35 to less than 40 would be this class. And that percent based on our data would be 14.9%. Now, if I wanted that as a decimal instead of a percentage, I would move that decimal to the left 2 times, which is where that 0.149 would come from. So let's use this relative frequency distribution to answer some questions. And this is where you may want to pause the video, try it, and then come back and check out your answers. So in part A, we want the percent of subscribers who are required at least 25 seconds to download a file. At least 25. So if we're looking at least 25, at least means greater than or equal to. So that would be this piece of the distribution. So we would add all of these up. So if I add all of those, I ended up with a 69.1. So based on our data, that probability would be 69.1% of subscribers need at least 25 seconds to download a file. B is asking the probability that a subscriber chosen at random will require at least 5 seconds, but less than 20 seconds. So let's figure out what part of the histogram we really need to, the frequency distribution we really need to focus on here. We want at least 5, but less than 20. So if I were to write that, as a mathematical statement, it would look like this, where I'm looking at numbers between 5 and 20. So between 5 and 20 would be these three classes. And if I were to add those up, 1.7 plus 4.3 plus 9.2, I'm going to get 15.2. So 15.2% of those that we collected data from here require between 5 and 20 seconds to download a file. You can see that's where our answer would come from there. So let's look at normal distributions a little bit more, and we're going to talk about something called the empirical rule. So normal distributions happen a lot in nature and in different things like birth weights and um, standardized tests and such. Like SAT tests are normally distributed. Weights of newborns are normally distributed. Weights of leaves of trees are going to be normally distributed. We're going to have a lot of things that's going to have this nice bell-shaped distribution. So with a normal distribution, like I said, it's going to be a bell shape. It's going to be symmetric about that middle, and that middle is going to be where that mean is. And they're talking about a population mean in this example because of that Greek letter mu there. Symmetric means if I were to fold this graph along that dotted line, the left-hand side and the right-hand side would match up. And we're looking at things that are normal. It does not have to be exactly matching up, but should be pretty close. Going back to our example up here, you can see that this is an approximately normal distribution because it's got that nice bell shape around it, and it's approximately symmetric about that mean. It's not exactly symmetric. We've got a little bit of a discrepancy, but it's really close to a normal distribution, which means we could apply something called the empirical rule. So let's dive a little bit more into the properties of a normal distribution before we talk about that. So a normal distribution is going to have certain properties. We talked about the symmetry. It's going to be symmetric about that middle, which is where that mean's going to be. And it turns out with a normal distribution, the mean, the median, and the mode are all going to be equal or approximately equal to each other. The y value of each point on the curve is the percent, and we're going to express that as a decimal of the data at the corresponding x value. So we're relating all of this really to something called area. And we're thinking about that total area under that curve. If we have this normal distribution, it turns out that that total area under the curve is going to add up to be 1, which means if I'm looking at area to the left of a certain value, and we could think about it in terms of a z-score, which we talked about in a previous video, then this area over here can be related to probability. So we could find the probability that some z-score is less than or equal to some number, and it's going to be that area that's over here. And the areas under the curve are going to be symmetric about the mean. And what that means is that if this is my mean, which is in the middle, then that area on the left has to be equal to the area on the right. And we would have 50% in each of those, because remember that total area has to add up to 1. So let's look at an example. Let's say we have this normal distribution here, and we know that the mean is 8, which means that this thing is going to be centered around x equals 8. They're telling us that this area here is going to be 15.9%. And as a decimal, that would be 0.159. So to write this as an inequality, what this means is that if I'm looking at the probability of x values being greater than or equal to, this would be 10 in this case, 10, then that probability is that area under the curve, which is 0.159. Another way of saying that is that 15.9% of all the data values that's greater than 10 would live in this region. That's what that region is representing. Now, if I know this region, then I could figure out what this region is. We know that the total area has to equal 1, and I'm trying to figure out what this is. So if I take that total area of 1 and I subtract what's going on that right-hand side, then that will tell me what's going on the left-hand side. So 0.841 would be this area on the left. So I have 84.1% of data values less than or equal to 10, and I have 15.9% of data values that are greater than or equal to 10. So all of this is leading us to something called the empirical rule. The empirical rule is a rule that's for normal distributions, and we're talking about values between 1, 2, and 3 standard deviations from the mean. And the empirical rule says that 68% of your data is guaranteed to be within 1 standard deviation of the mean. And what that means is if I were to take my normal distribution, and then this is my mean, and I'm going to use sample stuff here. If I were to go to the left and to the right, 1 standard deviation, I'll use S for standard deviation since that's what we're talking about with a sample. And I were to go right 1. Whatever these values are, I'm guaranteed that 68% of my data has to live in that area. Now, because we've got some symmetry here, then I know that half of that would have to be here and half of that would have to be here. And half of 68 is 34. So 34% would live here, 34% would live here for a total of 68 between those values. If we are within 2 standard deviations of the mean, then we would expect 95% of our data to live within that, whatever those limits are. So let's go another standard deviation up and another standard deviation down. So if we know 95 has to live here between whatever this number is and this number is, and we know 68 is here, then that difference would be divided between these two places. So 95 minus 68 is 27, and 27 divided by 2 is 13.5. And then if we're talking about 3 standard deviations, we expect 99.7% of data to fall within there. So I'm going to go 3 standard deviations here. So this would be x bar plus 3 times the standard deviation because I start here and I would move 1, 2, 3 standard deviations above. And then I'm going to move from here 1, 2, 3 standard deviations below. So we would expect 99.7% to live between this number and this number, whatever those numbers would be. So if this is 99.7, and we know from here to here is 95, then that difference has to be divided equally between here and here. So that difference is 4.7, and if we divide it by 2, you zoom in a little bit, we're going to get 2.35 here, and then 2.35 here. So you can see how we're taking this and we're splitting it between all these little pieces, or we can split it between the little pieces. And then all of this, from 3 standard deviations below to 3 standard deviations above, is 99.7%. all of it has to add to 100%. So that leaves us 0.3% left over to split between the tails. And if we divide that by 2, I'm going to get 0.15% for each. So that's how we can take that normal distribution and split it up. If we have anything outside of 1, 2, or 3 standard deviations, we cannot use the empirical rule. This is where we would use technology. If we wanted something that was 2.7 standard deviations away, or something that was 1.3 standard deviations away, we could use technology to help us figure out what that area under the curve would be. But for right now, we're just going to stick with 1, 2, and 3 standard deviations. So how do we use this rule? Let's look at an example. Take a minute, read the problem, and then come back and we'll talk about it. We have a survey of 1,000 U.S. gas stations that found that the price charged for a gallon of regular gas can be approximated by a normal distribution. That lets us know we can use the empirical rule. They tell us that the mean is 310 and that the standard deviation is 0.18. We want to know how many gas stations charge various amounts. So in part A, we're looking for between 2.74 and 3.46. I'm going to start by drawing a picture. I know the mean has to be in the middle. And I'm going to use the standard deviation to go above the mean and below the mean until I hit these numbers. So I had 18 cents to get 3.28. And then I'm going to go another standard deviation. So I'm going to add another 18 cents. And that's going to put me at 3.46. And then, so that's my upper. That's what I'm looking for there. So let's go the other way. We're going to take 310 and we're going to subtract a standard deviation, which is 18 cents. So we're going to get 292 there. Now I'm going to subtract another one. And then I'm going to get 274. So I went 2 standard deviations to the left and 2 standard deviations to the right, which means I am 2 standard deviations about the mean. Our empirical rule says that we would expect 95% of all gas stations to fall within those 2 limits. I don't know why we're at 275 there. That's 274. So 95% of those gas stations would fall between that. So to figure out the number, because it's asking how many, I'm going to multiply it by 1,000. And then I'm going to get 950. So we would expect 950 gas stations to have gas prices between 274 and 346. Let's look at B. B wants to find the probability that we are less than 3.28, $3.28. I'm going to start by drawing a picture. So here's 310. If I go 1 standard deviation above, I'm at 328. If I go 1 standard deviation below, I'm at 2.92. We know that if we are looking at 1 standard deviation about the mean, which means we're moving to the left and to the right one, this would be a total of 68%. We want to find the probability first that we are less than 328. So let's think about what we know. That 68% would have to be split evenly between here and here. So I would have 34% here, and I would have 34% here. Let me write that as a percentage instead of a decimal. Now, I also know, because this is symmetric and that 310 is the mean, that all of this is really 50%. So I could think about all of it grouped together as 50%. I want to know all of this from 328 down. So I'm going to take that 50% plus that 34%, which would be 84%. So it's going to be 84% of the 1,000, which would be 840 gas stations. Then that last one, we want to know more than $3.46. So again, we're going to start with our picture. Mean is in the middle. If I go up 1 standard deviation, I'm at 328. If I go up 2, I'm at 346. Likewise, if I went down 2, I would be at 274. So we know that if we are within 2 standard deviations of the mean, then we would expect 95% of our data to fall within these values. We're looking for more than 3.46, $3.46. So we're looking for this area here. So we can find that by using properties of normal distributions. We know all of it has to add up to 100%. We know the stuff in the middle is 95%. So that leaves 5% left to split evenly between each tail. So if I divide that by 2, I'm going to get 2.5%. So I would have 2.5% in that right tail and 2.5% in that left tail. I want to know how many. So I'm going to take that 2.5%, turn it into a decimal, and then we're multiplying by 1,000. And we're going to get 25. We would have 25 gas stations that fall in that category. So what if we can't use the empirical rule? What if it's not 1, 2, or 3 standard deviations away from the mean? That's where the standard normal distribution is going to come in handy. So it's going to be useful to take our x values and then turn them into z-scores. And remember, a z-score is the x minus the mean divided by the standard deviation. It doesn't matter whether it's population or whether it's sample information. So converting these to z-scores normalizes all the x values so that we're really focused on the standard normal distribution that's going to have a mean of 0 and a standard deviation of 1. And if the normal distribution, the regular distribution was normal, then when I look at all those z-scores for each of those values, it's going to be normal also. So we're creating a standard normal distribution there. So it takes something that's not normal and puts it on this standard normal curve. So then the question will become, what do we do? How do we figure out those percentages? Because now we're not talking about 1, 2, and 3 standard deviations away from the mean necessarily. So the standard normal distribution has a mean of 0, and it's going to have a standard deviation of 1. When we talk about our normal distribution, and I'm looking between A and B, we could see it written like this. Thinking about that probability or that percentage of z-score values that would live between that lower bound and that upper bound. And we can use technology to help us find those values. Now I'm going to show you how to do this in Desmos. So let's look at an example. A soda machine dispenses soda in 12-ounce cups. Tests show that the actual amount of soda dispensed is normally distributed with a mean of 12.01 and a standard deviation of 0.09. So there's my mean, my standard deviation, and I'm going to use sample. It doesn't matter whether I use population notation or sample notation here, because the z-score is going to be the same. Z-score is going to be x minus the mean divided by the standard deviation. We want to know what percent of cups will receive less than 12 ounces of soda. So we're looking at the probability that X is going to be less than 12 ounces. We've got to find the z-score associated with that. So z is going to be equal to my X value minus the mean, and then we're going to divide it by the standard deviation. And because that X value is slightly less than that mean, then we're going to get a negative number. So I got negative 0.01 divided by 0.09, and that's going to be equal to negative 0.11. So this is equivalent to saying I need to find the probability that the z-score is less than negative 0.11. So let's figure out what that's going to be. So we're going to go to Desmos. So I typed in n dot normal distribution, 0 and 1. Now how to fix that? It's just normal distribution, 0 and 1. Okay, so that's the mean and the standard deviation, and they tell you that there. We want to know the probability that we were less than negative 0.11. So less than is going to be the left-hand side. And then negative 0.11. There's our probability, 0.456. So we would expect 45.6% of cups to get less than 12 ounces of soda. B is asking us what percent of cups will receive between 11.95 and 12.1 ounces. So we're going to write that as a mathematical sentence. So we want that X value to be between 11.95 and 12.1. And then we've got to find the z-score associated with each one of those. So z, let me do it in different color. Z is equal to my X value minus the mean divided by the standard deviation. So I got 11.95 minus 12.01. Now I'm dividing that by 0.09. I got negative 0.67 for that. And then we're going to do the same thing with that other one, 12.1 minus 12.01 divided by 0.09. That's going to give me a z-score of 1. So this is equivalent to saying we want to find the probability that my z is between negative 0.67 and 1. Okay, so a graph, 0 would be in the middle. Negative 0.67 is here, 1 is here. I'm looking for that area under the curve. With that last one, it was a less than problem. Here's 0, and my z-score was negative 0.11, and I'm shading to the left of that. But this one's an in-between problem, so when I go to Desmos, I need to use that inner feature. So negative 0.67 and then 1. And you can see that area is 0.59. Or 59%. And then let's look at that last one. We want to find the probability that the machine is going to dispense more than, so greater than 12.05. We're going to find the z-score. So 12.05. What's going on with my tablet? Minus the mean divided by the standard deviation. I got 0.44. And I'm rounding the z-scores to 2 decimal places, but we could go 3 or 4 decimal places if we wanted to be a little bit more accurate. So z is greater than 0.44. So if I were to think about a picture, standard normal distribution, 0 is in the middle, 0.44 is to the right, and I'm shading everything greater than, which would be that area. So let's go to Desmos. Now I'm looking at the right side. And that's going to be 0.33. Or 33%. So that's how we could use the normal distribution to help us solve problems.